Hello, today's topic is nonlinear dimensionality reduction. Actually, in the previous chapter, we talked about dimensionality reduction algorithms, especially linear methods like PCA and MDS. And LDA is actually dimension reduction algorithms with labels. Okay, so in this chapter, we're going to talk about nonlinear method for dimension reduction. Okay, so especially we're going to talk about the kernel method and the manifold learning. First of all, we're going to talk about kernel trick. So when we have a PCA, then we can generalize PCA with the kernel. Okay, and then when we have a Fisher discriminant analysis, then we can generalize or we can extend Fisher discriminant analysis with the kernels. Okay, likewise, when we have ICA, then we can think of kernel ICA. And whenever we have a linear method, then we can think of kernel something. Okay. And the next topic is manifold learning, which was so popular in 2000. Especially we have three most popular algorithms, ISOMAP and LLE and TSNE, stochastic neighbor embedding. So ISOMAP and LLE were the most popular manifold learning algorithms at the beginning of this manifold learning research. But usually, recently, people use SNE. So we're going to cover these three algorithms in detail. And then in nonlinear dimensionality reduction algorithms, we have kernel-based algorithms and manifold learning algorithms. And at the end of this process, finally, we have a neural network-based algorithms. Okay, so there is a big difference between the kernel-based algorithms and neural network-based algorithms. And we're going to discuss some differences and issues about these algorithms. Then what is a nonlinear dimension reduction? So as you know, what principal component analysis does, right? So in PCA, we project all the data samples into a hyperplane like this. And this projection is really a linear, okay? So all the points will be projected in the same direction. But in the principal curves or kernel PCA, these two are kind of extension of PCA. And in these algorithms, the samples are projected into hypersurface. It's kind of curved surface. And in this case, the direction of these projections are different. Look at this one, and this one. These two lines are pointing different directions, right? So this is a good example of nonlinear dimension reduction. And we're going to extend all this linear method with the kernel trick. So as I said in the outline, we can extend. So the extensions to nonlinear dimension reduction with the kernel trick. So we can think of kernel PCA, and given the Fisher discriminant, we can think of kernel Fisher discriminant. So we can come up with the kernel FD. Likewise, we can extend all this linear method based on the kernel tree. So kernel PCA and kernel ADA and kernel ICA. And we didn't talk about linear regression, which will be covered in the next chapter. And this one can be extended to kernel regression too. So basically, we have a linear method and we have a kernel tree, and we can think of this kernel somethings. Now we have to talk about nonlinear mapping, right? So as I said before, with the principal curves, the projection map is not linear, which means all the points are projected in the different directions, okay? So let's think about this nonlinear mapping. Given this x, which is n samples, and we can think of this nonlinear function phi. And one data sample xi belongs to d-dimensional space. We multiply n because we have n samples. So each sample is in d-dimensional space. Okay, so this function phi is mapping a data sample in the d-dimensional space to f feature space. Okay, and we don't know how many dimensions we need for this feature space. It could be infinite dimensional space. We don't know. Okay, then what is the benefit? When we have data samples like this, so we have a couple of red dots and blue dots, and let's assume that this is a classification problem. And then this classification is a little complicated, right? So this is not linearly separable. So something like this curved line is necessary to distinguish these red and blue dots. Okay, so let's assume that this classification boundary is complicated. Then we can think of this nonlinear function phi, and based on this function, we can map these dots data samples into some feature space. It could be high dimensional, okay? It could be lower dimensional, it doesn't matter. To understand more easily, let's assume that we are thinking of higher dimensional space. So in this case, three-dimensional. And then if we can come up with the really nice nonlinear function phi, then in this feature space, these points will be separable. Okay, there is an assumption here. If this nonlinear function is great, okay, then we have a perfect feature space for the task. And this feature space has a k-dimensional. And as I said, k could be infinite, okay? And the important thing is that in this feature space, the task would be much simpler and easier, okay? Again, we don't know how to define this phi, but let's assume that we have a nice phi. Then everything is perfect. Okay, then we have to apply this nonlinear function to all the data samples. So from x to phi of x, then these data samples will be in, this one is actually a matrix, and then this one is in k times n matrix. So again, from d times n, we transform the data matrix to k times n matrix. Still, we have the questions. How can we define the nice function phi? And here's a trick. We are not going to define the function phi, okay? We will not define. Even we will not use that function at all. So this function is kind of imaginary function. We invented this function, but we don't use this function. This is trick. First of all, to talk about this kernel trick, let me talk about this important concept. Many machine learning algorithms are based on relationships between the samples. These relationships can be implemented by inner product or distance. So as always, in the machine learning algorithms, we have to define the dissimilarity or inner product. Okay, so anyway, we have to provide some kind of metric to define the relationship between the data points. If you come up with new machine learning algorithms, then explicitly or implicitly, you define the similarity between the samples. You define the relationship between the data samples. Okay, now we're going to talk about kernel tree. A binary function, kernel k, can take the role in the feature space, this. Let me explain what kernel tree does with this figure. So in the input space, we have 2 points, x and y. And this input space is really complicated, and we don't like this. So we can come up with a new function phi. Again, we don't know how to define function phi, okay? But let's assume that there is a function phi. And this function phi is really nice, okay? Then we have to transform x to phi of x, y to phi of y. And then, as I said, in most machine learning algorithms, the algorithms are defined by the relationship between the data samples. And most of the time, these relationships can be implemented by inner products or distance. So let's assume that we use inner product. Okay. Do you remember in the PCA, we use the covariance matrix, and also we could use inner product matrix, right? So PCA was defined based on the inner product. Likewise, many algorithms can be rewritten based on the inner product. Okay, so now let's assume that inner product defines the relationship between the data samples. Okay, so since we transformed these samples to the feature space, okay, now what we need is an inner product in this feature space. So after mapping based on the phi, then we have to apply the inner product. So then what we need is inner product in the feature space. Okay, and this one is actually a scalar. Think about the inner product when we have a two vector. If we apply the inner product between these two vectors, then we're going to get one scalar. Likewise, this one is a vector and this one is vector. So we apply the inner product between these two vectors, then we will get a scalar value. Okay, so far we assume that we have a nice function and we applied inner product. So from x and y, we got this value. Good. This is a traditional process, but a kernel trick will avoid this complicated step, these two steps. Instead, kernel trick will use one function, binary function k, and k will take two vectors x and y, and it will generate one scalar value like this. So that's why we call it trick. In the logical process, we have to map these vectors to the feature space, and then we have to apply the inner product to get this inner product. But instead of transforming all the data samples, then we just skip. We just use kernel trick to go directly to this. So this is trick. Then now we have another question. How can we define this kernel function? Is it the same kind of questions? In the previous case, our question was, how could we define this nice function? That was the question. Now we have another question. How can we define this kernel? Then k is the binary function, but all the binary functions cannot be a kernel. So there is kind of constraint. There is a requirement to be a kernel functions. Remember when we talked about distance? So mathematically, to define a distance, we have to satisfy a couple of conditions, like the distance between 2 points should be positive, and if the distance is 0, then x and y should be at the same point, and it should be symmetry, and it should satisfy this triangle inequality. So this kernel defines the relationship between data points, and the distance defines the relationship between the data points. So basically, they are talking about the same thing from different perspective. Okay, so if we need some constraint to define the distance like this, then we need some constraint to define a kernel function. Okay, then what kind of requirements for the kernel functions do we have? To talk about these requirements, we have to talk about the Mercer's theorem. So it says any positive semi-definite kernel can be expressed as an inner product in some space. Again, if kernel is positive semi-definite, then this kernel function is actually an inner product in some space. We don't know what kind of space it is, but it is an inner product in some space. So the constraint is that this kernel should be positive semi-definite. This one is actually equivalent to the conditions for the distance. So we talked about three conditions. And then this positive semi-definite is equivalent condition. And let's look at this theorem. So if a kernel function is positive semi-definite, and this one is positive semi-definite. Remember that x, k, x is positive for all x, then k is positive definite, right? So we use different style to represent these things. Think about this one as a vector and this one as a vector with different values, okay? So if we change this x, then f of x will be a vector and f of y will be a vector, and k of x, y will be kind of matrix. So basically, this one is the same thing. But in this case, f of x could be in an infinite dimensional space. But in this case, it's a little hard to imagine that kind of situations. But basically, they are talking about the same things. Okay, then there is eigenfunctions phi sub I, such that this kernel is actually an inner product between two vectors in some place. Okay, so do you remember in the previous slide, if we have a nice function phi, then we can replace this function plus inner product with a kernel, right? And in this slide, if we have a kernel which is positive semi-definite, then implicitly there is a nonlinear function phi and the inner product. Again, as long as kernel function is positive semi-definite, then it can be a kernel. So to help you understand what this theory says, okay, and let me take some examples. So given two vectors x and y, okay, then let a kernel be a square of inner product. So we just defined a kernel functions. So this is binary functions. Binary function means we get two inputs. And then this one is a scalar. Okay. Then we can rewrite this kernel in this way and then rearrange the terms and then rearrange one more time. Then we have inner product notation here. And then if we put this one as phi, okay, then we have inner product of phi. Again, let me repeat one more time. If the kernel is defined, and then this is positive semi-definite for sure. You can check that. And then we can derive this nonlinear function. So in this case, yes, this function is really simple so that we can come up with a nice function phi. But in general, when we define a kernel functions, then it's not that simple to come up with a nonlinear function phi. Okay, so in this case, this kernel function is really simple. So in this slide, what I'm saying is that by defining the kernel function as this, we implicitly define phi like this. Okay, so let me repeat one more time. If our function phi is defined by this, okay, then we transform x and y. So we have a phi of x and the phi of y. And then we apply the inner product between phi of x and the phi of y in this feature space. And then this one is exactly the same as k of x and y. And in this case, function k will be x and y square. I started from these functions, and then we can come up with this kernel function. But in practice, we actually define the kernel function first. And then we don't think of these nonlinear functions. So this nonlinear function is used implicitly, okay? And we don't actually derive exact nonlinear function, okay? So in this slide, I'm going to just show you if we have these positive definite kernel functions, then there is a nonlinear functions. But in general, it's not necessary to see these nonlinear functions, okay? So we just define the kernel functions, and we assume that there is nonlinear function, okay? And then applying this kernel function to 2 points is corresponding to the inner product between phi of x and phi of y. Again, we don't use nonlinear mapping phi, we just use kernel functions. But when we use kernel functions, implicitly we use nonlinear function phi. And there are a couple of popular kernel functions, okay? So polynomial kernels like this, or sigmoid kernels like this, and radial kernels like this, and then Laplacian kernels, And basically, Gaussian kernel looks like this, and Laplacian kernel looks like this. And we can make kernels from kernels. Like if we add two kernel functions, then this one is another kernel function, which means this one is positive definite and this one is positive definite. Then if we sum, then this one is positive definite. It's quite simple. X k1 x is positive definite and x transpose k2 x is positive, then plus means x transpose k1 k2 x. Yes, this one is positive definite and this one is positive definite, then the result of this sum should be positive, and which is exactly the same as this one. So if we use k, then the k should be positive definite. Okay, then if we multiply, then this one is positive definite too. Again, the kernels are all about the relationships between the data points. And usually they put more emphasis on neighbors. Look at this one. If they are close enough, then they have high value. And if they are far from each other, then the kernel value will be really small. So as long as they are close, then the kernel value will be high, which means we focus on the neighbors. Think about this one. Data points are like this. Then the kernel looks like this in two-dimensional space. Then this point will have some impact on these points. But look at this point. And the impact of this point to this point is almost zero, as much as this one. So this one and this one, in the Euclidean distance, these two distances are completely different. But in the kernel values, this one is almost the same as 0 and this one is almost the same as 0. So we don't care much about the data samples who are far from us. And we focus on the neighbors. Okay, that's what usually kernel functions do.